Hey guys, welcome to System Design Fight Club. I'm going to go over chapter 3, my prediction for what's going to be in chapter 3 of Alex Shu's upcoming book on machine learning system design. I don't have a copy yet because it hasn't actually been released yet. So I'm going just off of the titles that have been released in one of his blog posts. This is all I have for trying to predict the content of the chapter. For resources on figuring out this problem, I have the following from Wikipedia. It's basically going to be just a image recognition thing for it's like facial recognition. That's been around for years. That's been around for quite a while. It's just well, not recognizing whose face it is, but like recognizing that there is a face in the picture and where it is in the picture. In fact, one of my roommates in college even had a project where he just kind of used something like OpenCV for just kind of spotting the face in the picture. That's why I have it there. I even have a picture of how that kind of looks. It's this, and then you can see at the bottom, automatic face recognition with OpenCV. It's been around for years. I mean, figuring out how it works is going to be pretty tricky, like explaining how the facial recognition will work. But I mean, that's within a component. This isn't, it's we're talking about machine learning system design, not just machine learning itself. So I mean, I'm not really going, I don't care about glossing over how the actual facial finding part works since it's within the scope of system design. So the requirements are going to be that an input image will have faces blurred out in the output image. I think it's talking about whole people. I'm going to say faces because faces is the most well known. It's like that. That's why you want to blur it, is that you want to like have their identity anonymized. So I'm going to just say faces, but he's probably referring to the whole thing. But the facial aspect has totally been around for like maybe even more than a decade, I think. So call outs, there's obviously going to be a really huge chunk talking at a very high level about something like a convolutional neural network or some kind of model that was cutting edge back in 2016 or so. It's probably going to be a feed forward neural network, not a recurrent neural network. So it's really not that impressive. These are actually some things that I heard about back when I was in college myself, and I graduated like more than 5 years ago. So it's there's a lot more interesting stuff out there, and this is not the most sophisticated stuff in the world. The design for this problem was actually really straightforward. It was actually the easiest of all the chapters when I was trying to guess how it was going to look. But when I finally drew the diagram, I was like, hey, this is probably absolutely not what he's actually going to have in the book. And so I tried to like kind of, there's no way he's going to have anything that has as many components as mine, or like he's not really going to do availability and decoupling and a lot of the other stuff. So I decided to take a little bit of a different approach today, where I'm going to kind of work backwards. I took my approach and then I like kind of started simplifying pieces until I got to something that I would actually imagine seeing in Alex Shu's book. And that's what you have right over here. And I'm going to show you how to get from this thing to the kind of diagram that I would draw. I actually started with diagram 6 was what I originally drew. And it was just very much like, this is not what's going to be in there, obviously. This I can see. What we have here on the left, I can totally see happening in his book. This totally looks like a diagram that he would totally have just like straight out of the book. But that's not what I would do. It's you need to throw in some message brokers and stuff. And I'll walk through like one step at a time. I got 6 diagrams right up here. I'm going to show you gradually how you would turn it into what I actually had originally drawn. Yeah, I still want to go back into the call out, is that I feel like this is going to be a big opportunity for showing off how great they understand CNNs, convolutional neural networks. Yeah, this is a list of things that would actually impress me. There's so many articles out there on convolutional neural networks. I bet there's stuff out there that like actually explains it better than he's going to have. It's really not going to be that phenomenal. I mean, he's probably going to have a really good explanation of CNNs with a lot of pretty diagrams, but it's like that's been done before. It's not really impressive. It's not really new. There's so many other books that just explain it so much better, and will actually show you how to do it with like a toy project or something. So anything with recurrent neural networks, you're not going to find that anywhere in the book. Autoencoders, I hope that actually gets mentioned even in passing. Autoencoders, I think you kind of use them like PCA. principal component analysis. Deep belief networks are pretty cool. That was something that caught my eye back when I was in college. You can make them by stacking restricted Boltzmann machines, I believe. I think these are also something that's more on the unsupervised side. I gotta double check that. I remember like reading about them in some manner when I was in college. I might have even had to I might have seen them in one of the PowerPoint presentations in one of my classes or something in passing. So deep belief networks would be really cool. Image restoration was actually already a thing when I was in college before they started having. It's actually a little bit older than the stuff that Google is coming out with around 2019, like by a fair amount. There was these other things which are over here that I think got associated with how to do image restoration. It was not quite like, hey, we're gonna white out this big chunk. It was more like you had a fuzzy, grainy image, and it would have it like resolve back to the original, and it would have an original copy of that image, but you would give it a dirty one, and it would have a bunch of memories stored of a bunch of different images, and then it would have your provided grainy image resolve to the closest image stored in its memories. That was kind of cool. And that was also like probably recurrent neural network type of thing where it's not purely feed forward. That's why I don't think CNNs are impressive, is that they're not, it's a pure feed forward network. Is you just stack it a whole bunch and then you have the convolutions that are copied. It's feed forward. That's like not really impressive at all. It's been around for just so long. Okay, so there's that, and then there's also like the attention problems. I think that's kind of from a winner takes all network. Here's some more stuff associated with those terms. Those are pretty cool. I'm pretty sure there's some recurrent stuff going on. Restricted Boltzmann machines. Yeah, I never really learned those in depth. I think GANs are the things that you saw where it was like induced. It was like the first things with like induced hallucination on like images where it would like start throwing eyeballs everywhere, I think. I should double check that. I might be 100% wrong, but I just remember them being, generative adversarial neural networks. I think that was what that was. Generative adversarial neural networks. Yeah, adversarial. That's a huge word. Adversarial is a very hot word. That's much more cutting edge than CNNs. Adversarial neural networks, totally more cutting edge than convolutional ones. LSTMs are like a little bit recurrent. You could, before ChatGPT, this was a popular means of doing text generation for like stories and stuff. You would either do, it was like you had Markov chains, and if you wanted to go like one step more advanced than that, you started to see like LSTMs were like one more step more sophisticated than Markov chains. They're getting rather old though. They were like kind of cutting edge around 2017, I think. They were still pretty hip back in 2017, I think. So I'd still be impressed by that, but there's no way we're going to see that in the book. Prologue actually impresses me. I'm going to dig into that more in a second because I have some spicy comments to say about this. But first, hey, applied reinforcement learning without any hand waving. If we could have that, that would actually impress me. That would actually impress me. I did try to cover that actually with, I think, chapter 4. I took a stab at it because I was like, I want to have at least something that takes a stab at applied reinforcement learning. It was not the most appropriate chapter, or it was not the chapter that aligned the most with where you might potentially see reinforcement learning. But I decided to take a stab with it on that problem just because I was finally maybe getting the hang of it a little bit there. But yeah, that would impress me. Applied reinforcement learning, no hand waving, like in depth, in a real chapter, not just taken out of context and talked about in like theory, like applied to an actual system design problem. That would be cool. Like I have no idea how to host this. I have no idea how to host a reinforcement learning like model. Now time for the spicy part, prologue. Yeah, it impresses me. It's a language. So we're not able to like, so prologue isn't like an orthogonal approach to machine learning. It's currently like very orthogonal to machine learning. And we don't really, it's from this like field kind of called, I think it was like Scruffy. It's like the Scruffy approach, which was really popular in the 80s. And then it died out when and machine learning kind of took over, where it was more of a intuition building approach than this thing where you just have this big database of facts called a knowledge base. And I have an example of one of those knowledge bases right here, Psych. It's one of the biggest ones, I think. So ChatGPT is machine learning, and it suffers from the common sense knowledge problem. I have a link to that right here. This is a great explanation of common sense knowledge. ChatGPT definitely can't handle common sense knowledge, and an example of that is this right here. If you wanted to say, I have 2 carrots, 3 apples, 5 bananas, how many fruit do I have? Well, the answer is 8, because you have to recognize what is a fruit and what is not a fruit. ChatGPT is not able to extract knowledge like that. It doesn't have common sense knowledge. It's just a very fancy Markov chain, to my understanding. It's just a very fancy Markov chain. So it's not able to apply the stuff from like a knowledge base like Psych. Mixing those two things together is actually something that I've been very fascinated by for years, but you need a doctor to actually be able to even attempt any of that stuff. So it's yeah, that would impress me, is common sense knowledge within a machine learning context. Which this is where it gets spicy, is that Alex Shu, of course, did a blog post on ChatGPT, and I think this is it right here. Yep, there it is. So I mean, this is probably sure whatever, and it's fine for like ChatGPT's context for trying to apply it. This though, this right here, this text, 2 + 2 is equal to 4. That is not a good use case for ChatGPT. That's not. Try out a bunch of examples of adding together large numbers that are represented as words. So you could try like, maybe try feeding it 3,672 plus 89,765 is, just try out a bunch of different numbers. You don't have to do that many. It'll probably just be like a dozen. I've already seen it screwed up a lot of other stuff. Like I've definitely seen it screw up just which number is greater than the other. In some context, it was like in the context of some short story problem, it screwed up just doing a greater than less than comparison. It couldn't actually handle seeing whether it was like 1-digit numbers too. It was just a 1-digit number. It could not handle a greater than less than comparison, because it actually doesn't know what those numbers mean. It doesn't actually like pull out those numbers and try to plug them into some kind of math thing. And since it's just a very fancy Markov chain, it's not actually doing the math. It's trying to find a word somewhere that actually has the answer given these 2 words. So it's the rest of the post, sure, whatever. I mean, that's fine. I don't really care. This little bit here and this little bit there, that's not really what ChatGPT is just phenomenal at. It's a poor example. It's a poor example because it suffers from the common sense knowledge problem. And I just really had to talk about that. It just really got under my skin a lot. Yeah. We can go back to the what we're actually here for today, is that again, this problem. So the data model you'd use for it, it's probably convolutional neural network, which is a type of classifier. It's a classifier. So OpenCV has something great for that. I already talked about that. It was the image right here. And OpenCV, it probably even tells you like where the face is. So it's, instead of just true or false, it has a face, it tells you where the face is. Very epic. You go into the diagram though, you're probably going to see this. I'll give you an explanation of what's going on. So you got this picture capture service, and like as the Googler is driving around in their white van, I just really liked my wording there. They're gonna have these like pictures that are going off and getting snapped, and they're going to, I was thinking maybe you would do a multi-part upload on an S3 bucket. This will be an object store, of course. So you would first do a hit here, and it tells you, hey, we got this S3 bucket, you can put it in, and then it does the multi-part upload over here, and then it sends the ACT, the picture capture service, And then when that's done, it can go ahead and send any metadata related to the picture, such as its ID, and the URL will get stored over here. And you can see that in my picture. And then, so there's the metadata you write, and then you can go ahead and pass things forward to the next service. This is where I put a message broker. I don't think he's going to have a message broker, but then he would pass it over to here. And this thing is now going to take that picture and it is going to use the data model to figure out if there's a face in it or not. It can say true or false there, and then it's going to find it. And then still on that worker, it is going to go ahead and blur that face out of the image and then go ahead and store it again. And then it can go ahead and go further downstream, like pass the image ID further downstream. And so you have, there's a name for this little pattern of passing the image ID and not the actual full image file. I forget the name of it though, but that's what's going down these very thick lines is just the image ID itself, just the image ID, not the full image file. The image file is staying over here. You're just passing an image ID. Okay. So that was that's what I bet you're gonna see. The first thing that I would do is split this worker thing into 2 steps. It's doing a whole lot right now. It's doing a pretty long task. So I would split it into 2 steps so that it's a little bit better for retries. It won't have to restart this whole possibly 5-minute long task. I don't know how long it would take, but it's doing a lot here. And so you can split up the heavy amounts of work, try to split them down the middle. So I'm going to move on to this. I added my little hooks to make it look a lot more like how I usually do my diagrams. So I'd split it like this. You have the OpenCV work of finding and identifying the face in the picture is here, and it'll store where it is in this picture metadata. Oh, I didn't have that extra data in the schema. Whoops, sorry. And then the actual blurring work, the actual transformation of that image, given that metadata, would occur in a separate worker. So this one just is like, hey, is there a face there? Where is it? And then stores it in the pic metadata, and then it sends it up further upstream. So you still got this multi-part upload, tells this guy to do the thing, pulls in the picture, uploads the metadata related to whether or not there's a face to there, pass it upstream. This one pulls in the picture. Well, it actually first will pull in the metadata to see if this is a thing that needs some blurring work. If it does, pull in the picture, and then store the blurred picture, and then pass the image ID further downstream. So third, I was feeling that I might want to split the pic metadata DB. I was really on the fence with this decision of whether or not to split the metadata DB. So that's why this is the second more distinguishing piece that I'm going to do. And then I'll do this thing with orchestration and message brokers. That's much more what some people would call too much detail or just overcomplicated or something. I wouldn't. That's not how I feel, but that's what some people might argue. And so that's going to happen after it. But that's something I feel more confidently about than splitting the metadata DB. So here it is, splitting the metadata DB. Here I actually have that stuff in the schema that I forgot to add in the last picture. Well, okay, so I guess in the last picture, you don't need to store it in. Oh, yes, you do. Yeah, okay, you did need to store it in there. Whoops. Okay. So now we've got it split. So you have this one, it pulls in the pic metadata that was written by this. And then it does its little pull in of the original picture. Does it have stuff? If so, write it over to the image flag store, which is just for flagging whether or not it contains a face. And if so, extra metadata there, pass downstream. This one is the blur worker. Pull in the first. Check the image flag store. If it's a thing that needs blurred, pull in the original picture, do the blur work on that area of the picture. Because if you just flag it, it's what is it going to do? Blur the entire picture? I don't think it should do that. It should blur just the area that it looks like OpenCV is able to pick up on. It had boxes drawn on the image. So I think OpenCV can tell you exactly where it is OpenCV is not going to actually blur the image though. So there's that. So again, blur worker picks up a message, check the flag store. Is it a thing that contains a face? If yes, pull in the original, do the blurring work, write the output, pass the image ID upstream. Okay. Next, orchestration and message brokers. Here it is. So that was more of a choreography approach. If you just add in the message brokers alone over top of where those thick lines were, I would call that an orchestration approach. I would call that a choreography approach. So right now it's doing choreography. If you just add in the message brokers, it's doing choreography. I prefer orchestration. It seems like this is something that would stay within the domain of possibly one team, or it's the services seem the worker like tasks seem related enough that one team would probably be taking care of this. Or like when you're setting up this feature, like you would probably know that these two workers are going to have to like be there. So like you can take more of a top-down approach in the design. Choreography, I think, is just something that like arises more like naturally when you're not trying to plan the whole thing and you have these little features getting introduced one at a time within a pipeline, just extra steps getting accumulated over time to a pipeline. While this is when you like know what the whole pipeline is going to look like in advance. And so it's going to coordinate it. And message brokers before and after to make this work async. Let's talk through the full request flow. So first, the Googler and a van, they're going to ping the service. They're going to receive a pre-signed URL to upload it to. They're going to do the upload, the multi-part upload, ping the ACK over here. Then the picture capture service writes the metadata, puts a message on the queue, and then it can return back the 200 success. And so that makes all this async. This is the message broker that I feel is like the most crucial here. I mean, this blurring stuff is definitely not something you should have happening synchronously with the picture capture service. Like this is kind of important here. Maybe not the orchestration. Sure, you can argue that, but this message broker right here between the picture capture service and the face finding work. So like that would be right here. This would be a really crucial message broker to have, I feel. Even in approach one, I mean, it would be, I'd be really happy if Alex Shu threw in a message broker there. That would like definitely put him up by like a notch in my book if he had a message broker right there in that design. Okay, so we've put the message on the queue. Now we got the orchestrator, which will pull in the pick metadata, and then it'll go ahead and send stuff off to task one. And then this one is just doing the same stuff that it did previously, where it has the pick metadata from the orchestrator, it passes that along, and then it pulls in the original picture, given the metadata, which will tell it what the URL is. And then it'll, does it contain a face? If so, where? It'll write that over to the image flag service. And then it can go ahead and return a 200 response and tell it to go on to the next step. So the orchestrator proceeds to the next step. Each step is kind of like its own AWS Lambda function. It's like its own, each step is like a Lambda function. And so it's very fault tolerant. Each step is just kind of run like a separate request response thing. So that adds fault tolerance here. So the second step starts up, it has to read the pick metadata back in because it's kind of like it could actually be handled by a completely separate machine than the first step. So it has to read this back in, and then it's going to go ahead and call the blur worker. And so this thing is going to receive that metadata, and then it's going to check the image flag service. Hey, does it contain a face? Do I have to do some blur work? If so, pull in the original picture, and then it does the blurring work. And then it goes ahead and it writes the blurred picture over here when it's done, and you get a 200 success. Give that to the orchestrator, and then it goes ahead and it kicks off a message to downstream services to do whatever the heck they're going to do with the blurred picture and within the context of whatever Google Streets pipeline is. So then your downstream services that do stuff with those blurred pics, like putting them like up on the site or attaching them and hooking them into the Google Maps interface And there are other data stores. So it will now know like, hey, here's the image ID, and here's where you can find it, where it picks. So it can do a read off of here, and it'll do whatever else it is doing downstream. After that, I added in a training pipeline. I really don't think Alex Shu is going to cover training pipelines, but I like to go deep on these things. So that's all that's getting added here. This is all that I've really added here is the training pipeline. It's like, how does that data model get there? That's what I wanted to answer here. How does that data model get there? I think I also finally numbered my steps for these, but I walked very detailed through the request flow in the previous picture, so I'm not going to go over those again. Yeah, that is the first time I added it. Okay, so it's just over here is all I've added. You're going to have some kind of, how does the model get there? Well, you have a model store. That's a common thing. In my content-based problems I've covered, I similarly had a model store, but this is also good for when it's not content-based filtering where you have user-specific models. It's also good for just A/B testing. So whenever you train up a new model, a new classifier, you'll write it to the model store, and then you'll slowly dial it up to, you'll have two setups of the face finding workers. You'll have a A set and a B set, a treatment and control set. And the control is what was already there before. And then you'll set up a new cluster of workers for the treatment step. So you run a deployment to that new cluster. And then you slowly will switch over the handling from the treatment workers to the control workers. The control workers will receive more of these requests over time. More of the requests from over here will start getting sent over to the control cluster than the treatment cluster. But yeah, you run a deployment to a new cluster, pulling it from the model store, and you're just deploying the data model with the executable file. And that model object could be something like a Python pickle file. That's a good call out actually, is models can be stored as Python pickle files. And that's just, you can just do like import pickle or something, just look up Python pickle and you'll be able to find what I'm talking about. After you train up a model, it's like running in RAM. You got to persist it to a file. And it's like, well, how do I store this thing in RAM, this like binary Python object as a thing on disk? And so pickle's one way to do that. So this is just a bunch of pickle files. You'll take it, you'll deploy it with the model, then you'll have something like maybe Flask or Django. And if you train the model in Python as well. And so you would just send it off with your executable of the Flask or the Django service, and you deploy it with the pickle file, kick it off, and it'd have a reference to that file to pull into memory, kind of similarly to a Java bean. So you pull these in similarly to Java bean. Yeah, just on startup, you don't pull it like multiple times. It just like you pull it into RAM once and you're good to go. How do you get the stuff in the model object store? Well, so you're gonna have to train stuff up. You'll have this label training data, labeled training data. You need some data for training your classifier. So you're gonna have this long running job for training the model. That's probably actually gonna be the longest running worker task in this whole setup. This you can take hours or weeks to train some models, particularly with image recognition stuff on like a Tesla, or text generation on some occasions takes multiple weeks. I actually heard of an LSTM model in production at one of my previous companies that took multiple weeks to train. They completely misapplied it to the problem. It's just supposed to do generative text, but that's a tangent. But yeah, these can actually take weeks to train. And so then when it's done, you definitely want to stick it into a file, persist it, get into that model object store. Yeah, so that's what I added here. Next diagram, I added in CAPTCHA. Oh yeah, that's another thing I wanted to cover is where are we going to get that labeled training data? Well, I feel like CAPTCHA. So this is a really simplified view of CAPTCHA though. Yeah, I mean, it's not actually what we wanted to focus on in this problem. But I thought it'd be fun to cover. So like, for example, there's you filling out a CAPTCHA, you receive unlabeled training data. Maybe it's partially labeled to check whether or not you're actually a bot. So that way it can tell you, nope, invalid CAPTCHA and make sure you're not just spamming random entries. So maybe it's partially labeled just as validation, but you're gonna have this unlabeled data mixed in. You're going to help, it'll record your responses, and that'll help with determining whether or not it is one label or another, as opposed to Google hiring a whole bunch of contractors to label stuff for them. They're just kind of crowdsourcing it. I have some fun stories about what you used to be able to do to screw with CAPTCHA. You used to be able to, you used to know which data was labeled versus unlabeled, and so you could easily just type whatever you want for the unlabeled stuff and just intentionally feed it bad data. I used to enjoy doing that actually. And then the data from your responses and the unlabeled data is going to be used for, it's going to be turned into labeled data, of course. It's going to pull in your response, it's going to pull in the labeled data, it's going to do some thinking, and it'll figure out it'll figure out what class to label each data point, each image that you were it was trying out on people. It'll figure out the class, and it'll also do feature extraction, which I've covered in other videos. That would actually be interesting, that the feature extraction aspect where you actually there's probably PCA involved there. But it's going to figure out the labels, and it's also going to do feature extraction or data cleanup work, and then it'll write it over here, and that's what they'll use for training the models, and they'll roll it out to the model store. Yeah. But this is my final diagram with some extra stuff. If you go back to over here, that's probably the same scope. This is keeping it restricted to the same scope as AlexShoe. And then I just added in the pipeline and then CAPTCHA. But this is the same scope without any extra fun additional scope items. I think I've covered everything I want. Yeah. Yes, I have. Okay. Well, thanks for watching. Yeah, see you next time. See ya.